So this lesson is really just about practicing constructing Taylor series and also practicing our tests for convergence. So basically steps are going to be, we're going to work out the derivatives. We're going to determine the values of the coefficients. Okay, so we're going to do that expansion. And then we want to try to generalize the formula for those coefficients. So this part here, I'm just going to put a little star here. This tends to be the hard part. Some of them are easy, some of them are hard. Okay, and so once we've done that, we can then determine the Taylor series in the sigma notation form with our sigma notation. And then once we've established this, we can then do a ratio test and test for convergence for this new series. Okay, so let's set up a Taylor series for this cosine function. Okay, so the Taylor series then again is going to be, we're going to make our polynomial. So we're going to start with a equals 0. Okay, so the first term is going to be the cosine value. So it's the function established at the center 0. Okay, and then we're going to do the next term, a1. So this would then be the derivative, and maybe we should just, we use a formula over 0 factorial. So the next term is going to be the derivative. Okay, so it's going to be cosine. Sorry, the derivative of cosine is negative sine. Negative sine evaluated at 0 over 1 factorial. Okay, this will generate the sequence term, and the polynomial term is going to be then x to the power 1. Okay, and then we're going to go plus a3, and as we go along, I'm going to just start evaluating some of these coefficients because how we may not have to use that many terms to establish. So generalizing the formula for the coefficients. Okay, so let's establish this. Cosine of 0 is 1. So 0 factorial is 1. That's going to be negative 0. Okay, so that's going to be plus 0. So we're going to skip that term. So then the a3 term, we're going to differentiate sine. We're going to end up with negative cosine. So negative cosine of 0. And then over 2 factorial. And this is going to be for x squared. So we're going to be minus cosine of 0 is 1. 2 factorial is, I'm just going to maybe leave that as 2 factorial. Okay, and I'm going to leave that as 0 factorial. Now, the only reason I do that is because it's going to be easier to then, I can see that there's going to be a factorial pattern. So it's going to be a little bit easier to establish the general sequence or the general formula for that. Okay, so I'm going to go to the next one. So derivative of negative cosine is sine. So sine 0, okay, or negative sine. So we end up with positive sine. And so we end up with over 3 factorial. Okay, so that would be our a4. And that's going to give us, okay, that's going to be basically 0. So that's going to give us 0x cubed. So we're just going to put down 0 here. And I'm going to do maybe a couple more here. So plus, so this is going to be my a5. And you may already start recognizing that every odd term is going to be the ones that we're going to use. Okay, so this is going to be cosine of 0 over 4 factorial. And so we're going to end up with x to the power 4 on this one. 2, 3, sorry, we missed 2, didn't we? Okay, 2, so it's going to be every even term, my mistake. So it's going to be every even term is going to generate a term. So this becomes 1 over 4 factorial, okay, and then x to the power 4, etc. So plus dot, 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 plus dot, 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 dot. Okay, so looking at these coefficients then, we can see that it's going to be, well, we really just going to start with 1 over 0 factorial, 1 over minus, so it looks like it's alternating. Okay, it's going to alternate every second term like that. We're going to skip terms, so we need to be able to skip terms, which means that every second term we're going to need to use a 2n formula for this. Okay, so then my p of x is going to look like this. So I'm going to start it at 0. Okay, sometimes I might want to start it at 1, but in this case I think we're going to start it at 0 because we have this 0 factorial here. So it's going to look like this. I'm going to have x to the power 2n. Okay, because I know that I'm going to have a power at 0, a power at 2, a power at 4, etc. So this is going to be x to the power 2n. And then the factorials seem to match. The denominators seem to match the power, so that's perfect. I can just then do 2n factorial. And then I also have to notice that these are alternating terms, so I do know how to alternate things now. Okay, so I know that I'm going to have a negative 1 to the power n. And just make sure that my power n is going to give me the right positives and negatives. Yeah, it's going to start with an even. So 0 is going to give me even, or sorry, a positive. x2 is going to be my next term. Okay, so now I'm basically going to renumber these and start off like this, and this is going to be my a1. Okay, so I'm just going to maybe do this in a different color. So I'm going to renumber these because since every n represents 2 terms, this is going to end up being it converts to a1, right? These ones disappear. This now converts to a2. Okay, so a2 is going to give me a power of 4 and 4 here, and again it's going to go from even. So a1, 0, 1 will give me a minus, a2 will give me a positive, okay, a3 will give me negative, etc. It looks like I have the right formula now. So I had to account for a few things here, this plus minus, and also the fact that now we're getting rid of terms. I have to skip terms, so I need to renumber them to make sure that I get my n's right. So there it is. There's my general formula. So there's my Taylor series formula. Once I've established that, I just need to test for when is this valid. Okay, this function is going to be valid. I need to do a test. So I'm going to do my ratio test. So limit as n goes to infinity. I'm going to set my ratio. Negative 1 to the n plus 1. This is going to be x to the 2n plus 2 when I substitute n plus 1 into there, over, squeeze this in a little bit more. This is going to be 2n plus 2 factorial. And the denominator is going to be negative 1 to the n, x to the 2n, and 2n factorial. Just shorten that up a little bit. And I want that ratio to be less than 1 for this to converge. So rearranging this and grouping some of my terms together, I'm going to group my negative 1, so I'm going to end up with negative 1 to the power 1. Group my x's, so x to 2n plus 2 divided by x to 2n is just going to leave me with x squared. Okay, with the factorial part of this, I'm going to end up with 2n factorial over 2n plus 2 factorial. Okay, so it's nice to understand the factorial here. I have 2 more factors in the denominator than I have in the numerator. Okay, so when I simplify that factorial out, so n goes to infinity, I'm going to end up with negative x squared, and the 2n factorials, I'm going to make them cancel out by writing 2n plus 2 factorial like this, 2n factorial times 2n plus 1 times 2n plus 2. Okay, so that's equivalent to 2n plus 2 factorial. I can make that less than 0, cancel a few more terms out. Canceling those terms out, I think I can now establish my limit. Okay, so as I let my limit go to infinity, this denominator is infinite. So basically, when I work out my limit, I get negative x squared over 1 over infinity, so times 0 is less than 1. So what number times 0 is going to be less than 1? Any number times 0 is 0, so that's always going to be less than 1. So here we've established that our radius is going to be x is all real numbers. Okay, so we have an infinite radius here, and we don't even need to test endpoints. Great, I'm done.